Let me begin with a word of prayer. So let me pray first here. Dear Father, we thank you for this day. Again, I thank you for this class. I just ask you to bless our work. Help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. So I guess I didn't have this on our list of topics or whatever, but it occurred to me it wouldn't hurt us to spend 10 minutes talking about it. And so here we are. So I want to talk about topological groups just a little bit. And this is, again, based on, whatchamacallit here, John Lee's Topological Manifolds book, page 77 to 80, something like that. And so here's the definition. All right, so if you have a group G with multiplication, let's say M, which is a mapping from the Cartesian product of G with itself back to G again, and inversion, let's say inv G maps to G, right? So like typical notation, M of G comma H equals to GH, and the inverse of G is, well, G inverse, right? Although you do also sometimes have additive groups where the multiplication is addition, and the inversion in such an additive context would be negation. All right. So the concept of a group is there's a binary operation which is associative, and it's closed under inversion. So a group with multiplication and inversion is a topological group. If G is a topological space with continuous M and inv. So a topological group is simply a group which is also a topological space, and the operations are continuous. All right. So some examples. The reals under addition with the usual Euclidean topology. The reals with multiplication, that's not quite right. Let's say here, the reals without 0 paired with the usual multiplication. Again, the Euclidean topology. So the first one's an additive group, the second one is a multiplicative group. This is oftentimes called R star for just non-zero reals. Third example, non-zero complex numbers. What would the group operation be on that? Multiplication, right. Of course, you could also, this is not in John Lee, I guess, but V over a vector space over F, right, is an additive group. And certainly if it's finite dimensional, right, if it's finite dimensional, we can choose a basis, and with respect to that basis, we can build an inner product. All right, so any finite dimensional vector space can be made into an inner product. Once you have an inner product, you can define a metric. Once you define a metric, you can define a metric topology. And with respect to the metric topology, the finite dimensional addition and negation, those are continuous operations. So any finite dimensional vector space can be viewed as a topological group. Now, infinite dimensional vector spaces, there's terms and conditions applied to there. I think you can have infinite dimensional vector spaces where the addition might not be continuous with respect to the topological structure. That's possible. But people also talk about topological vector spaces, which I'm guessing is assuming that, well, anyway, you guys can study that later. But in the finite dimensional context, it's certainly fine. We talked about this a little bit already, but like GLN, right? The n by n matrices with non-zero determinant, right? So first of all, we can view those as I mentioned to you guys the other day, I think, this is what? The inverse image of the set what? Minus infinity to 0, union with 0 to infinity, right? That's all non-zero numbers. And the determinant defines a continuous map from the n by n matrices to the reals, right? So if this is a continuous map, you can prove it. This is continuous with respect to the usual topology, like the Euclidean topology of the reals, and if you like, the Euclidean topology of n by n matrices. Given these terms and conditions, the determinant is a continuous map, and for that reason, GLN is the inverse image of an open set, right? Open. And as such, this is an open subset of our n by n. And we can take, by the way, if you have any, so here's a general thing. If you have a topological space, all right, if you have a subset of the topological space, you can make it a topological space in and of itself, right? So I think Jack, you and Preston know this from topology, right? Like if I have X is a topological space, and so like that's the topology on X. If A is a subset of X, I can define a topology on A simply by using the subspace topology, and it is simply formed by what? A intersect U, such that U is in the topology on X, right? And that defines a topology on the subspace. So because GLN is a subspace of the n by n matrices, it is itself a topological space. So this is a topological group. Another example, SLN, right? That's the inverse image under the determinant of 1. So this is a closed, as a subspace of our n by n. It's a closed subspace of n by n, but it's also a topological group. Because matrix multiplication and matrix inversion are continuous. The fact that matrix multiplication is continuous should be fairly evident. Why is inversion? Do you guys understand why the inverse of a matrix, why is that a continuous operation? So the reason for that is there's a formula for the inverse, like A inverse. It's 1 over the determinant of A times the classical adjoint of A transposed. That's a stone cold formula for the inverse, and it's formed simply by a reciprocal of product of the components of A, and this is nothing more than a matrix of it's a matrix of determinants of the minors. So like that is the matrix you form by taking so if A is n by n, you look at n minus 1 by n minus 1 submatrices. the ijth component of the adjoint, you take the ith row and the jth column, cross them out, take the determinant of the resulting n minus 1 by n minus 1 matrix, put a plus or a minus in the entry, and that's the component of the adjoint. So the adjoint is made, it's a determinant of it's a matrix of determinant of submatrices of A, and you're dividing by a determinant of A. Everything here is a product of components or difference or sum. Those are all continuous in as much as they're defined, which is the context here. So that makes inversion continuous. Another example of a topological group is the n-torus. So this is the n-torus, and what's the group product here? It's the product with the product multiplication. What's that? So if I have like, A1, A2, an times B1, B2, bn, how do you multiply them? Well, you just multiply them component by component, right? Well, you guys are, wait a minute, Shane, are you in abstract right now? Okay, so yeah, you guys know what I'm talking about. Although, I don't think Sprano has a lot of time devoted to matrix examples, if I understand. No, his thrust has always been much more in terms of like dirty number theory examples. They're dirty. He makes them fun. All right, so let's see here. So just to talk a little bit more here. If G is a topological group, all right, there's another thing we can define. You can talk about left translation. By G in G. So the left translation by G in a topological group is, well, it's just multiplication by G. All right, so like L sub G mapping from G to G. All right, and here's how it's defined. L sub G of X is just equal to, GX.
This thing scared me in complex analysis for some reason. It's so simple.
What's that?
This whole left translation thing scared me in complex analysis.
Ah.
But it's simple. It just scared me for some reason.
Oh, the way yeah, okay, yeah, that's true. I just talk about the, that's right, left multiplication in C. I do that there, that's true. Forgot about that. So why is that continuous here? So you can argue.
Well, the action method?
Oh, no, nothing. Like.
Isn't the input is X?
So to be.
Output is just a constant times X.
Well,
What's that word?
I'm assuming G is a topological group. That's all the structure we have to work with here, okay? So like, to be more methodical, I should say this is X maps to, this is really the multiplication of G and X. I guess so that.
If it's already a topological group, then we know that the multiplication is continuous.
Right. So I know that the thing is, I know multiplication. So this is like a restriction of the multiplication, right? Where I'm freezing one of the inputs. This is for fixed G, right? But anyway, so it is continuous, and I'm sorry, I'm belaboring this way more than I should be at the moment. This is, after all, not a full topology class, so we don't. All right, so, but here's the interesting, oh man. So definition. X is topologically homogeneous. What would that mean? Topologically homogeneous. If for any x and y in X, all right, there exists a homeomorphism phi from X to X, all right, with phi of X equal to Y. He says, intuitively, this means that X looks the same from any vantage point, all right? So in a topological group, you have this homogeneity, right? So so if this is, you guys tell me, if this is the group, right? And here's the point X. I want to get over to the point Y with a homeomorphism. What do you think it would be? How can I go from here to here by some phi? Phi, what's the formula? Phi of what? Phi of X equals to what? What's that?
X equals Y.
I guess I should do it for an arbitrary point, right? X and Y are fixed here. Let me say for G. So phi of G equals to what?
Under G. H.
GH?
No. Isn't this just saying that if there's a I'm thinking of homomorphism.
How about this? What if I do this? What happens when so what is this? This is, so if you plug in X, what do you get? Right? And is that, I would argue that you can prove that that's continuous. This is a continuous map because it's formed by, a product of a, fixed element. Yeah. So that's actually a right multiplication, I guess. Oh, I'm sorry. I should have been. It's not wrong. It's just not right. I should have done this. I should have done Y. I should have done YG X inverse there. If I did that, the other one wasn't wrong. It was just not what I wanted to do. So then I'd have like Y X X inverse, which is still equal to Y, right? But then this, I guess it's, well, I don't know. Whatever. I mean, I'm assuming it's associative too, right? Technically, I need parentheses and stuff in here. Let me not belabor this too much. The point is that this is a continuous map which goes from X to Y. And why is there an inverse? What's the inverse for phi? If I set this equal to H and solve for G, what do you get? Right, so like phi inverse of H is Y inverse HX. You can check that that's an inverse for phi, right?
Even associative.
Yes, but this is a group, so we know it's associative, yeah. And if you believe me that the first one was continuous, then that one's obviously also continuous, right? The point is, in a topological group, any 2 points are, you know, there's a homeomorphism from one point to the other, right? So topologically speaking, all points on a topological group kind of look the same, right? That doesn't have to be the same. That doesn't have to be the case in other topological spaces, right? Like if you look at the wedge sum of the axes we had last time, there's definitely a distinction between the intersection point and other points, you know? But if you look at the plane, right, then topologically speaking, every point on the plane is the same, you know? GLN, topologically speaking, looks the same everywhere, all right? I mean, are different points in GLN different? Well, absolutely, right? The identity is very special, but it's not very special topologically speaking, you know? So, in this sense. So, and then, then he talks about group actions. Did you guys ever talk about group actions in abstract? Group actions. I don't think so either. So let's talk about group actions. You guys should hear about what a group action is. So, what is a group action? So if G is a group, not necessarily a topological group at the moment, and X is a set. All right. A left action of G on X, all right, is a map from G Cartesian product X to X again, all right, written as the follows, like you have G comma X maps to, let's say, G dot X, usually an X, a dot there for the group action, all right? And it has the following properties. All right, number one, it's kind of an associativity, but it's not actually associativity. G1 dot G2 dot X is equal to G1 G2 dot X, all right? And that has to be true for all G1, G2 in G and X in X. And number two, I'll let you guys tell me what happens here. 1 dot X is equal to what? I heard an X. You hope so? Well, you were correct. You were close now. So of course, you guys might look at this as E dot X equals to X. The E being for eins element.
Eins ketchup.
Yeah. No, we don't like that. Eins ketchup.
You don't remember my spring break escapade?
Oh, that's right. That's right. Oh, yes. So this is a group action, all right? So if you guys, and this oftentimes, I don't think Sperano usually studies this. This is one of those things you absolutely should study before you get to grad school, because this is like something everybody knows about, and it just doesn't always, we don't always end up covering it here. Because when he goes to 422, he tends to just go into field theory, and I don't think he usually circles back to this. So, I mean, there's definitely enough abstract algebra to teach like three introductory semesters. So, something gets left out by everybody. It just, you know. But this notion of a group action is important because it dovetails together with these deeper theorems of group theory called the Silo theorems. And so there's like a group action in the symmetric group. The permutation group is called the symmetric group. Sn is the symmetric group. Anyway, I'm telling you guys, there's a lot to learn there. So this is a left action. A right action on G is like the same thing, but the X and the G are reversed, okay? And it's kind of a matter of taste which one you use. If X is a topological space and G is a group acting on S, then this is called an action by homeomorphisms. If this is a homeomorphism, all right, if this is a homeomorphism for each G, and if G is a topological group, it's said to be continuous if the mapping is continuous. So, like this continuous. So he has a proposition. Suppose G is a topological group acting on a topological space X. If the action is continuous, it's an action by homeomorphisms. If G has the discrete topology, then the action is continuous if and only if it is an action by homeomorphisms. All right. So a little bit more here. G dot X is equal to G dot little x such that G is in G. All right. This is called the orbit of X. All right. And the action is said to be transitive if for any x comma y in X, all right, there exists G in G such that y is equal to G dot X. So that's what we mean by a transitive group action, is one that you can start wherever you want in the set X, and the group will take you to any other point. All right, that's a transitive action. In other words, the orbit of each point is the entire space. The action said to be free it's said to be free if the only element of G that fixes any point in X is the identity. That is, if G dot X equals to X for some X implies G is equal to the identity. A free action. So what are some examples of continuous group actions? All right. All right. So some examples of continuous group actions are GLN R X on Rn. So like, you know, we have A in here, we have X in here, right? And basically you can talk about the orbit. Orbit of X would be what? Like AX, right? Such that A is in GLN. What would that be? Seems like a good homework problem. Number 2, the orthogonal group, ON. What's the orthogonal group? ON, let me explain what that is. That's A in Rn by n such that, let's say it this way, A transpose A equals to the identity, right? This is,
Or your notation from the line right above this is not working. If you say orbit and then collision right after.
I'm at peace with it.
Okay.
But if you'd like, I could go back to glnr dot x, which was the notation over here. Yeah? But that's supposed to be one of those funny looking O's that doesn't quite close. Yeah.
Oh.
Yeah. Okay, so this is the orthogonal group. You can also let the orthogonal group act on Rn by matrix multiplication. All right? In fact, this would be a restriction of the group action from the previous one. Right? That's another thing you could try. If you have a group action by G, you could restrict to a subgroup H and still have a group action. Do you guys see what I'm saying? If G forms a group action on the set X and H is a subgroup of G, these axioms automatically hold for the subgroup. So any group action automatically defines a subgroup action for any of the subgroups of G. In that context, this defines a subgroup action of that group action. But things get interesting for the subgroup. The orbits could be not as big. Like when you guys study this properly, there are 2 orbits. There are only 2 orbits of the action in one. Whereas in case 2, there are infinitely many orbits. All right? Three, you can let the non-zero reals act on Rn with the origin removed by scalar multiplication. So like, you know, lambda times x equals to lambda x, you know, for x not equal to 0, and lambda an element of the reals. What would the orbits then be? He says the action is free. This is a free action, case 3. And the oh, my bad. This is actually 4 for him. He's got them lettered anyway. This is actually like D. His 3 was actually let ON act on the like n sphere. N sphere, n minus 1, n minus 1 sphere rather. This gives transitive action. All right. If you have gamma is a subgroup of the topological group G with the subspace topology, group multiplication on the left or right defines a right action, left or right action of gamma. So like you can, if gamma is a subset of G, then you can define I'll just say GX. But this is like interesting. He says, oh, it has to have the subspace topology. All right. So that would define a group that would define a group action of a subgroup of G on itself. So for instance, You know, it could be something like, for example, in this one, you could have something like gamma is the integer lattice, and G is, I don't know, Rn, for instance. So that Zn is a subgroup of Rn under addition, you know. And in this context, I would be talking something like, you know, like vector Z acting on the x vector would be what? It would be, you know, Z plus x in this context. That would be the group action like that. And Z is, Z given the discrete topology on Z is the subspace topology on Z. Because there's an open set that contains any singleton in Z. And this isn't Z, of course. This is the integer lattice. This is Z cross Z cross Z cross Z cross Z. But it's a grid of points, right? Any one of those points, you can put a little bubble around. And the intersection of the point with the bubble is just the point, which makes that an open set with respect to the subspace topology of Zn. So the subspace topology of a discrete set is the discrete topology on the discrete set. These things work together. All right. Let's see here. And then he goes on to talk about like factor groups a little bit. And let's see here. Maybe I probably should try to complete this thought. I know we're well past my 10 minutes. A little bit. Yeah. I tell you, I'm going to go straight ahead to the only example I care about. So this is example. This may not make sense because I'm jumping a bunch of definitions, but 3.92. Make sure to tell Professor Schmidt, if you see him, that my lecture was very polished and focused today. There's no rabbit chasing. Okay, anyway, as an application, let us consider the coset space. Fine. He says a particularly important special case arises when G is a topological group and we consider the action of a subgroup. The orbit fine. G is a topological group. Gamma a subgroup. All right. And orbit of the right action of gamma on G, right, is set of form what? G gamma, such that gamma and gamma. But can you guys recognize what this is?
A left coset of gamma.
Very good. That is the left coset G gamma. So the orbits of the right action are the left cosets. So thus the orbit space of the right action of gamma on G is, so the orbit space of the right action is, you know, G mod gamma, right? quotient space is called the left coset space of G by gamma. He said, it is unfortunate but unavoidable that the right action produces a left coset space and vice versa. If G is abelian, the situation's simpler because they're equal. Great. True enough. So here's his example. This example is the whole reason I wanted to cover any of this stuff, guys. So, because I just think it kind of dovetails with what we were doing last time. And here it is anyway. Consider the coset space R by Z. Right? He says, because Z is a subgroup of the topological group R, there's a natural, free, continuous action of Z by R. The natural translation n dot x simply equal to n plus x. Right? He says, because R is abelian, we might as well consider it a left action. Okay. The orbits are what? They're the equivalence classes. They're you know, x such that x is equivalent to y, right? I mean, this is the equivalence class of y, right? And this equivalence is what? X equivalent to y, if and only if what? Y minus x is an element of the integers, right? We looked at these sets before, right? In that example we looked at. He says, thus the quotient space is exactly the same as the coset space R mod Z. Consider the map. We look at epsilon, a mapping from the reals to S1 by epsilon of R is equal e to the 2 pi IR. He says this is a local homeomorphism and thus an open map, so it's a quotient map because it makes the same identifications as the quotient map R to R by Z. The uniqueness of the quotient spaces tells us that R by Z is homeomorphic to S1. All right. He says, more generally, the discrete group Zn x on Rn by translation, and by similar reasoning, we can, so like this map shows us that so the kernel of this map is what? The kernel of this map is the integers, right? And the first isomorphism theorem says that that defines a, you know, epsilon bar from R mod the kernel. This is a surjection, right? So this is in fact an isomorphism of the coset space and the multiplicative unit circle. But it's also a homeomorphism, topologically speaking. And the generalization of this, you can look at like epsilon, let's say sub n, mapping Rn to the n torus. What would the formula for that be? So we're doing like x1, x2, dot dot dot, xn. What should we do? Right. And then if we, what's the kernel of that? Is it, so I keep saying it's a homomorphism. Is that obvious to you guys? That's an homomorphism? Does that even make sense? So this previous one, the reason that this is a homomorphism in the sense of group theory is if I have epsilon of r plus s, I've got e to the 2 pi I r plus s, but by the properties of the imaginary exponential, that's e to the 2 pi I r, e to the 2 pi I s, which of course is epsilon of r times epsilon of s. As you can see, addition is preserved in the form of multiplication because we're going from an additive group to a multiplicative group. This one, same song and dance, every component, right? If I take the sum of two vectors, I get exponentials of the sums, which in every component I do the calculation above. So it's indeed a homomorphism. And the kernel of this, and by the way, it's a surjection, right? So the first isomorphism theorem of group theory tells me that the induced map on the quotient space, let's say epsilon sub n bar, from Rn mod the kernel, which is Zn here, is in fact an isomorphism of groups. But in this context, it's also a homeomorphism, which is to say that the topology of the quotient of Rn by Zn is the same as the topology of Tn. The n torus is, topologically speaking, Rn mod Zn. And also, in terms of the group structure, it's the same, going from a multiplicative in the torus to an additive in the lattice. I like it very much when these kinds of worlds collide, right? We're talking about really vastly different things at the same time, you know? Topology and algebra. There's, if you continue studying group actions, there's something called the orbit stabilizer theorem that you should look at, which is very interesting and allows you to solve problems that would be otherwise quite formidable. Maybe I'll try to make a homework problem that allows you to explore that in here, since you guys won't see it anywhere else. That'd probably be worth a few minutes of your time. I don't think it'll take long if I'm careful. So, sorry, if I was smarter, I would have realized we should cover a little bit of algebra in here earlier. I didn't know that everyone in here was either taking or had taken abstract. I was thinking, Shane, that like next year you were taking abstract or something when I was originally planning things, or I don't know, it just didn't hit me. Or maybe it's just the title of the course being advanced analysis. But you know, these distinctions between, you know, analysis and algebra, they become less meaningful as you go on. It's all just math. All right, so now on to the proposed topic for today. So, yeah, homework. Hey, I remember homework. So don't worry, Shane and Jack. I will make more homework. It's going to happen. It's going to. Well, Preston already has homework to work on. So I mean, I'm just trying to be logical, you know. Holy cow! Like Trump has made released some kind of whatever. I don't know if I feel like it must have been like yesterday or recently, concerning like what he's going to do his first day, and it's beautiful. It's just beautiful. Anyway. Something about, he's like banning all gender training in all different aspects of the government, like all of these various gender training programs. He's going to just kill them all. And make it federal law that they're just two genders. Like, ooh.
So we're good. Group actions to Trump actions.
Group actions to Trump actions. And to homotopy. No homo, though. homotopy.
What did you say? That doesn't register.
Clearly, it's homotopy. That's
Homotopy. No, I'm not going to write it. It's tempting, but no. All right. So, what is homotopy? Let me just try to talk about it sort of vaguely for a bit. So the concept. Okay. So first of all, topology. First and foremost, the question is of classification. You know, given two topological spaces, when are they topologically equivalent? Right. That's the first and sort of overarching, grand, glorious question of topology. Is, you know, if you have a topological space X and you've got a topological space Y, can you find, you know, a mapping F and a mapping with inverse, F inverse, both of these continuous? If F and F inverse are both continuous bijections, right? Then if that's possible, then X and Y are I can't spell. Homeomorphic, right? So, I mean, for example, and that really means, so F and these are both continuous, okay? So this is, of course, with respect to what? If we're talking about topological spaces, we're saying, you know, X has a topology, Y has a topology. Continuity is always judged with respect to these existing topologies. All right. So are two spaces homeomorphic? That's a central question of topology, and it's actually too hard of a question in many contexts. Like, it's just a little bit too hard to answer. We do have lots and lots of answers, partial answers to this question in many different contexts, but it is sometimes just too hard a question. A slightly easier question is, given two topological spaces X and Y, are they homotopic? So to say X and Y are homotopic means that, well, it's something like this, but it's a weakening of it, all right? So you, I don't know if I shouldn't try to define it just yet. I might not get to that today, actually, but it's a weakening of this, where you're not insisting on quite this. So before this, the concept of homotopy it's all tied around the idea of deformation, right? So much of what we so much of what we sell to high schoolers and so forth as topology is really homotopy, right? This idea of deforming one space into another, yeah? That's a homotopy. How do we make this precise? Well, we make it precise, first of all, by talking about homotopy of maps, all right? And so, let me jump ahead a bit. So I will send you guys a link to this. So to tell you where I'm working, where I'm working out of here. I'm working out of, oh, come on. Hatcher, yeah. So out of Hatcher's. Yeah, the first chapter is an amazing overview of all these ideas. It's really quite powerful. But this is actually the second chapter where he starts giving definitions and working stuff out. And we won't cover much, hardly at all. But this is actually from chapter 0, but he gives it in chapter 1 again. The general definition of homotopy. Let's see here. So, oh man, that's not what I wanted. Well, let's write it down. Maybe it'll be helpful. So, phi sub t, a mapping from X to Y for T in I. I, as usual, is the unit interval, all right? And the associated map phi from x Cartesian product the unit interval to y again. All right, and here the notation is that phi of x comma t is equal to phi sub t of x. So a homotopy is, he says, in chapter 0, he introduces a homotopy as a family phi sub t like this. And so this is the associated map. This has to be continuous. All right, well, it's fine. I think I remember the definition. So, I'm sorry, guys. I ran out of time preparing stuff today. This is fine, but let me just let me make a proper definition out of this. Definition: f mapping x to y and g also mapping x to y are homotopic if there exists continuous phi, all right, like this. And this right here is just notation, all right? This is just helpful notation where phi sub 0 of x is equal to f of x, and phi sub 1 of x is equal to g of x. In other words, if you like, you could just say phi sub 0 is f, and phi sub 1 is g. Okay? So the homotopy usually is referred to, this thing right here is itself the homotopy. Okay, this is the homotopy because it's laying out the ground map for how you deform the F map into the G map, and through a continuous morphing, right, going from one to the other. In this context, you say that, you know, F is homotopic to G, something like that. All right. So to say that X and Y, so I think I remember actually, so let me go for it, and I hope this hopefully won't be too much of a lie. So if you have, you know, if you have F going from, oh good grief, F going from X to Y, right, and you have G going from Y to X, right, and if you can show that F composed with G is homotopic to the identity, and G composed with F is homotopic to the identity over here, and what do you think the identity should be there? G is doing what? G composed with F is going Y to X to Y. So we're talking about the identity on Y in the first equation, right? And here we're talking about the identity on X in the second equation, right? So